Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience, who would be curating the RealSci_Nano Twitter account.
Hi everyone. Today we have with us Andrea Armani, who is a professor of chemical engineering and material science at the University of Southern California. Hi Andrea, how are you?
Great. Thank you very much for inviting me here today.
We are very, very happy to have you, and I'm very much excited to know more about you as a scientist, your career, a lot of things. I'm going to ask you lots of questions. So let's start by understanding your career journey so far. So please tell us how you got to be the professor at the University of Southern California.
So my career path is a little meandering.
Okay.
So we'll go all the way backwards. So when I was in high school, my high school wasn't like one of these stellar high schools with huge science programs. So I took biology, chemistry, and physics was the last class I took. So when I started looking around at colleges, I decided I wanted to be a physicist. And I applied to several schools, like every high school student does. And but I really focused on physics programs. So I went to University of Chicago and majored in physics. I discovered my first quarter there that I really was more of an engineer. But when I was in high school, I didn't know what engineering was. I didn't even know engineers existed. I didn't come from a science family. So now I was in a university that didn't have an engineering department, that didn't offer engineering degrees. And I was a first semester freshman. So I was looking, down a 4-year path of majoring in something I wasn't super excited about. But, thinking long term, the most important thing about college is to get a degree and get out and start working. So I, kind of took a deep breath and decided to get my degree and then start thinking about how I could pivot and use that degree to get into engineering. So I got my degree in physics. And then when I was applying to grad schools, I started looking at applied physics programs, which is really engineering physics. And so I took that path. I applied to both material science and applied physics programs and ended up going into applied physics. And by that point, I'd really discovered kind of my love of biology and really combining, engineering and biology. And so while I was getting my PhD, I also got a minor in biology. So I could really, not just dabble in biology, but really have an academic understanding of biology as well. And then when I started applying for postdocs, I also looked at chemical engineering as really kind of taking that leap into engineering. And so then I did a postdoc for 2 years in chemical engineering and biology, combining those two fields. So then when I started applying for faculty positions, this became a little bit of a quandary. Where do I apply? Do I apply to physics departments? Do I apply to biology departments? Do I apply to engineering departments? Where do I fit? And this is why I tell postdocs and grad students who are applying to faculty positions, don't limit yourself. Right? Look at your research. Look at where your research fits. Look at where your passion lies. And apply to all the departments where you kind of fit, because your research will evolve as your passions evolve. And you don't necessarily need to limit yourself to where your passion was when you were 18 years old, or 17 years old, because your love will change, right? And your research will change.
Right.
So I started applying to positions, and I ended up in a chemical engineering and material science department, which is obviously very different from where I started when I was 18 in physics.
Right.
And so that's my main appointment now is in chemical engineering and material science. And I have a couple joint appointments in electrical engineering and biomedical engineering and chemistry. So my research group is, all of those fields. It combines all of them. And I have students from all those different departments in my group.
That is
Yeah,
so cool.
yes, this very non-conventional, not straight path.
Absolutely, absolutely. But wow, this is so impressive. So it's, chemistry, physics, biology, material science, engineering, um, computer science, maybe also a
No,
little bit now that you have
no,
electrical.
yeah, my computer science skills are embarrassingly weak. That is my weakness. This is actually one of the best things about all of these online courses now, is
Mhm.
that you, like, someone, I hate to use this word, someone who's old like me, because computer science was truly, like, it was a baby field when I was in college. People didn't major in computer science. Like,
Right.
mathematicians would get like minors in computer science, because a lot of computer science departments were considered like subfields of math,
Yeah,
which seems really like strange now, right? Like, computer science are like entire schools of computer science.
right.
Uh, but then it was like a subfield of math. You might get like a minor in computer science, but it was really a science, like a true science. It was statistics.
Right.
So I never took any classes in CS, because I was like, I don't want to be a mathematician. uh,
Makes sense.
but
Yeah.
yeah, but now I can take all these like free online classes. So I'm learning a little bit of Python in my free time. I'm learning some R. So it's great.
Andrea, you have to stop somewhere. You have to leave some fields for other people as well. You're just
No,
everywhere.
but this is a great thing about being an academic, or really just being an engineer or a scientist, right? Like, you can always keep learning something new.
Right.
There's always something new to learn. You don't just get your 4-year undergrad education and then stop, right? Like, there's your undergrad education, like, teaches you how to learn and how to teach yourself, and it's
Hmm.
really like a springboard. Uh, and that ability is amazing. Uh, so that's yeah. So I'm now working on trying to fix my really embarrassing lack of computer science. You somehow managed to, like, hit the one thing that I'm most insecure about. So
You should not feel
congratulations.
embarrassed about it at all. You definitely should not feel embarrassed because you have so much knowledge already, and you're already um, acquiring skills with Python and R and all of that while being a professor, while supervising students, while doing all of this. So kudos to you because you have nothing to be embarrassed about. This is like, I'm more just afraid that you will turn into this superhuman sort of a person who knows everything from computer science to life sciences to natural sciences, everything, which is great. Um, but it's also intimidating.
Well,
But
thank
yeah.
you.
Awesome. So thank you very much for telling us
Mhm,
about your career journey. So your current research,
mhm.
you already spoke a little bit about that in the short podcast. But where does it fit in this big picture of materials or nanoscience, this
Yep,
very broad field that we have? So where does it
yep.
fit?
So I would say materials kind of forms the starting point or the foundation. So
Mhm.
whenever you think about a material, uh, if you invent a new material, that's really the starting point of an entire pipeline of technology development. So
Mhm.
in our lab, we take that same mindset.
Mhm.
So if we talk with physicians, or if we talk with engineers in the telecom field, they'll propose a problem. Like, they want
Mhm.
a faster modulator, or they want a better diagnostic, or they want a better way of imaging cells.
Mhm.
And so we really think about what that problem is. And then
Mhm.
we, go all the way back to the beginning, and we say, okay, how can we develop a new material that will then enable a better modulator, or a better frequency comb, or a better imaging agent? And
Mhm.
usually, like, you could take an existing technology and try to, like, tweak it, but that's really like trying to use a screw as a nail. Like,
Mhm.
you can do it, but it doesn't really work very well. uh,
Mhm.
so we'll say, okay, if we want a better imaging agent, let's think about how can we design a better molecule that can do higher efficiency two photon imaging, that's more biocompatible, that's smaller, that maybe has an easier, higher efficiency synthesis route, um, that maybe, like, self intercalates into the cell membrane. Um, and maybe has really good tunability in terms of its wavelength absorption, right? So like we think about like how can we develop a new material that has lots of different properties that the biologists want, and then we start with like DFT design of the molecular structure. So like very beginning, so theory, and then we design the synthesis, and then we actually make it, then we characterize it, and then after all of that, then we start moving into like biocompatibility studies with some cell lines, and then we actually do imaging studies and etc. So that's like an example project.
Wow.
That's like one line of investigation. A similar line of investigation might be, trying to develop a new material to develop higher efficiency frequency cones. And it would have that same type of process. So going back to the drawing board on designing a new material that would have better properties in different ways, and then designing that material for a device architecture, optimizing in an optical device, it would be for things like the nonlinear refractive index, the refractive index contrast, the compatibility with nanofabrication methods so that you could create planar arrays, and then also the dispersion of the material. So, taking into account the optical properties as well as the actual like manufacturing. So like the long-term like things you're going to need to consider. And then we, after we make the material, then we actually do the fabrication, we do the device characterization. So my lab has chemists in it to actually do that material design, and chemical engineers to, work with the chemists to do the scale up on the synthesis, and material scientists to do that. But then we also have electrical engineers and physicists. And we have biomedical engineers. So we kind of span all of that. So all of those fields.
Okay.
So it's a lot of fun.
It sounds like a lot of fun. I almost want to quit my current job and move back to science and ask you if you have an open position for me to do a postdoc or something. But no, that sounds really cool. So it's basically from theory to like from conceptualization to like to application, like the entire thing. It's not just like a bit of characterization, a bit of fabrication. No. You do everything.
Yeah,
From
it's the whole
start till
food
the
chain.
end. Oh wow,
Yeah.
that is really cool. You are truly a material scientist, I must say.
Yeah. No, so like it depends who I'm talking to. But some people know me for my integrated photonics work, and some people know me as a microscopist. Some know me as a chemist, because it depends like which section of work I'm known for.
Right.
And then it gets really awkward when two different people meet and they know me for different fields, and that gets very interesting. Or if I go,
go on.
Or if like I go, so for example, I went to Koç University in Turkey and gave a talk in the chemistry department there on a lot of our like optically responsive polymers. So the entire talk was about like the synthesis of the polymers and how they were UV cleavable, and we could use them as like a early warning for skin cancer. So like to prevent you from getting burned. But then in the audience was an entire group that does similar work for our integrated photonic devices. So doing like lasers and like completely different field. Because they were trying to build a testing setup, and we have like 4 of them in our lab. So then at the end of my talk, like 3 of them raised their hands and started asking detailed questions about like how we do waveguide coupling, what type of lasers we have in our lab, like what are our scan speeds. And those questions had nothing to do with the entirety of my previous talk. And so the chemists in the audience were kind of looking at me like, what are they asking about? Like, how does this have to do with your, ATRP reaction? Like, what does laser speed have to do with polymerization? And so I was like, okay, I'm gonna pull up a different presentation, and we're gonna run through the testing setup. Like, just one second. We can do this. So it was great, right? Like, I'm glad they saw that I was giving this talk in the chemistry department,
right?
And came and felt comfortable coming.
Yeah.
But the chemists in the audience were just kind of staring at this group of students like, okay, why are you asking these questions that have nothing to do with this present talk?
And how do you know the answers to these questions? Aren't you a chemist?
Yeah, right. Like, don't you do polymer work? So that happens. And
that's really cool.
Yeah, it's great, but I was also super happy that the students came and felt comfortable enough to do that. Because it's also how, like, you know, science should progress, is that, you know, people should feel comfortable enough to ask questions like that. And say, like, you know, I'm having problems, like, can you help me troubleshoot my testing setup? Because absolutely. You know, I'm happy to help people troubleshoot their testing setup.
Absolutely.
But a lot of times people, you know, are like, no, it's my thing. I invented. I'm not going to help you.
I will tell you all the parameters, but 2.
Yes, exactly. Yeah, I'll tell you everything except like the 2 important ones.
Exactly. Yeah, but I'm glad that this sounds really cool. So you basically speak polymer, you speak chemistry, you speak physics, you speak engineering, you speak electrical engineering, you speak material science. So you can speak all these kinds of different languages, and you understand the terms because that's the breadth of your knowledge.
But it's also a lot of fun, right? Like you have a, you know, science degree and you're now doing something totally different, and it's fun. It's fun to keep switching things.
Yeah,
and moving around.
Absolutely. I absolutely agree with you. So the next question to you, Andrea, is that it sounds to me that, I mean, of course, you have like tons of interesting research projects going on. And not just right now, but also in the past, you have been involved in a lot of very interesting research projects. This is a tough question. If you have to pick one research project that you're most proud of, or the most fun or quirky one, could you pick one and explain it to us in simple words in the section we call In Other Words?
Yeah. So you asked me this question before, and I told you that it depends on the day, and it truly depends on the day. Because it depends on either, like, if a student has come into my office and shown me new data that day, then suddenly that's my favorite project. Absolutely. Because I just saw new data. So that's my favorite project. Absolutely. And it has nothing to do with, is that actually my favorite project, or is that actually the project I'm most proud of? But I guess if I really think back, I could bin favorite projects in terms of a couple different criteria. So there's the first project there's a project I'm most proud of for a reason that has nothing to do with complexity. And that would be the first project I worked on when I was an undergrad.
Okay.
And that I'm most proud of it simply because it was like the first research project I ever did. Right. And so it was like my first step into doing science.
Relatable, totally relatable. Please go on.
Yes. And so that project was taking polymers that were there were diblock copolymers, which means you have 2 different polymers, which you can think of as like string. And then, you know, so 2 different colors of yarn, and then you tie them together at one end. So then you basically have 2 different types of yarn attached to each other. And then you create a thin film of this. So then you just have like an array of all of these things. And then depending on the relative length between these 2 different types of yarn and how thick your film is. So, you know, like you're icing a cake, right? How thick your icing is. That determines what type of patterns you get. And I was super lucky. My mentor, a person named Ward Lopes, he gave me a lot of freedom. Possibly more freedom than he should have. But he let me like take images of my samples on a TEM, on a transmission electron microscope. Keep in mind, this was in like the 90s.
Yeah.
So TEMs were they're always very expensive, but they were very, very expensive. So I got to make my samples. I got to use a spinner. I got to actually like cleave wafers and do like super thin silicon nitride films. I got to measure them using an ellipsometer. I got to use a TEM. This was also in the time when this was before like good cameras. So I had to like manually develop my own film.
Oh my God.
Yeah.
Right.
So like, because I'm old. So it was an incredible time. So that's like, and the project like worked. It did result in a publication. I wasn't on it, but it was an incredible learning opportunity for me because I learned about so much different stuff. So that was like one of my favorite projects simply because of the learning that happened. So another one of my favorite projects was probably maybe the second or third project I did in grad school. Simply because it was a collaboration with my husband. And like that's right, like it's always nice when you do projects that are collaborations. And it started off as a dare. So he and I were in different research groups. Yeah, right. So he and I were in different research groups, and I was in a group making microfluidic channels out of PDMS, which is a plastic. It's a squishy plastic. And you make these microfluidic channels by first having like a master structure. So kind of like if you're making like car parts or something like that, you have like an initial starting structure. A mold, right? And then you pour this plastic on top of it, you make the plastic solid, and then you peel it off, and now you have like the inverse structure. And that's how you make a lot of microfluidic channels. And he had just made this like super fancy optical device called a resonator, and it looks kind of like a mushroom. So it's like elevated off of the substrate. It has a lot of like three-dimensional features to it, but it's super small. So it's about the width of a human hair. All right, so it's super tiny. So, and it's also made out of multiple material systems. So part of it was glass, part of it was silicon, which means there's some material challenges in trying to make a mold of it because part of it's hydrophilic, part of it's hydrophobic. So like a surface chemistry to keep it from the polymer from sticking to that is kind of hard. So he bet me I wouldn't be able to do it. Right? Fair
challenge accepted.
Challenge accepted. So I was like, I got this. So my first try, I got 1. I mean, it was an array of 12, but I got 1 to work. I was so proud of myself because I had to first make the negative mold, and then I had to backfill my mold and get the positive mold. And I got 1 to work. I was so proud of myself because I won the bet.
Of course.
Then right, we wanted to characterize my version of his initial structure to see if it actually was also a resonator. It took me 6 months to replicate it.
That doesn't count. First one worked. That's what counts.
Yes, first one works. That's when that counts on me winning the bet. But the reason why it took me, and this is a learning experience, the reason why it took me 6 months to replicate is because the surface chemistry that I used the first time was something called trichloromethylsilane. And so TCMS. And then when I went to reorder the bottle, the manufacturer, even though it was the same part number, they changed it to be TMCS. So trimethylchlorosilane.
Oh.
So instead of having 3 chlorines, it had 3 methyls. And so it had a totally different surface chemistry. And it took me 6 months to figure changed something, and then my surface chemistry no longer worked, and that's why I was no longer able to replicate it.
How mad were you?
I was incredibly upset. But I figured it out in the end. And so I use this for my PhD students as a teaching lesson on why it's so important to write down everything you do. Not just part numbers, but part numbers and names and purities and concentrations and don't trust vendors because vendors will change things and not tell you. So
it's your science, which would be screwed.
At the end of the day, it's your science and your responsibility. So at the end of the day, it was my fault for not checking and just assuming. But yeah, so those are like very long ago. But then we just had a manuscript accepted yesterday in a journal. So right now that's my favorite project.
Congratulations.
Which isn't fair. Right? That's not fair to all the other work going on in the group. So
it's the most recent celebration.
It's the most recent celebration.
Exactly. Yeah. That is really, really cool. Really, really cool projects. And I actually love the part that you went all the way back in the first project and but I love it all. That is so cool. So Andrea, it's very, very evident to me that you really like the research aspect of being a scientist, doing
Mhm.
the probably, I don't know how much time you get now to go take the pictures, go to the lab, go to the wet bench. I don't know about that, but you really enjoy that. But other
Mhm.
than that, what else do you like about being a scientist or being a professor in your
Mhm.
case?
So I actually, when I first started grad school, I went to grad school planning on going to a national lab. Um,
Hmm.
and then I TA'd, and I TA'd actually my first and second year in grad school. So my first year I TA'd a grad lab course, and my second year I TA'd the grad version of nonlinear and non-equilibrium thermodynamics.
Mhm.
Um, so one was more of like a classroom, and one was a lab class, and I really enjoyed TAing, which
Mhm.
I fully acknowledge is not something most people say, but I really enjoyed it. And that kind of changed my decision on, do I want to be a professor or do I want to be a full-time researcher?
Mhm.
And so, that's my way of saying that the part I enjoy actually most about being a professor is getting to work with students,
Mhm.
seeing students grow, both undergrad students, high school students, as well as my PhD students and my postdoc. Like
Mhm.
actually seeing them, come into my lab, if they're undergrads, come into my lab, perhaps never having been in a lab before, not understanding how to develop controls for their experiments, perhaps never having used a microscope before. And then when they leave, they're fully functioning researchers.
Mhm.
They've developed a confidence. They aren't afraid to say, okay, well, I know how to use the UV vis, the fluorimeters, kind of the same thing. I can probably figure out how to use the fluorimeter. They have that mindset. Uh,
Mhm.
and the same thing with the PhD students. They come in. They're basically undergrads.
Yeah.
They're 3 months after getting their bachelor's degree. It's not like they're suddenly grad students on day one of their PhD program.
They're
Um,
babies.
yeah, they're babies, right?
Yeah.
But just seeing how much they grow over the course of their PhD, to the last year of their PhD, I expect all of my PhD students to propose one project that is completely independent, not a project I'm giving them, but one that they conceptualize and it's their idea and they actually execute it all the way to the end.
Mhm.
And I think that's super important to have that independence of thought and that they
Mhm.
aren't relying on me for every idea in every direction. Because, after you have a
Mhm.
PhD, you're going to go out in the world and you're going to be the leader, right? People are going to look to you to give them guidance.
Yeah.
You know, so while you're in my
Absolutely.
group, I want you to, practice that because I'm still here as like a safety net.
Right.
So you get one chance.
That is so cool. I mean, I'm so happy that we have professors like you who like teaching, who like to mentor students, who like to
Mhm.
give this freedom to the students, PhD students. I really like this idea of at the end of their PhD, conceptualize one independent project. You
Yep.
probably don't have to do it, but conceptualize it because that is very
Yep.
similar to what one would have to do after they
Yep.
graduate. That's
Yep.
what is expected.
Yep.
Exactly what you said. That's what the world expects from you when you have the PhD at the end of your name or doctor in front of your name, however the system
Hmm.
works in different parts of the
Yep.
world,
Yeah.
that people are going to be like, okay, now you do it and then you should be able to do it.
Yeah. No, and it's really hard to, sit in front of a computer and be like, okay, I'm going to come up with something new. And it can be very intimidating the first time.
Yeah.
So I think it's really important to do it once and to really think through, like, okay, I'm coming up with something new. Like, what am I going to need to do that? Like, what practice experiments am I going to need to do that? What are my controls going to be? What
Mhm.
resources am I going to need?
Right.
And to actually go through that exercise.
Yeah, absolutely. That is very, very cool. So, I mean, we did speak a bit about the advices and you compiling already the different kinds of life hacks or advices, however we call
Mm-hmm.
them. So, what advice would you give either to yourself if you were
Mm-hmm.
starting out today, or if for students who are starting out today, what
Mm-hmm.
advice would you give them? I mean, I know there's going to be tons of advice
There's so
coming. But yeah,
So
so have at
yeah.
it, please.
So one of my former PhD students, I found this out like after she graduated. She actually had an entire like notebook, lab notebook of like advice I've gotten from Professor Armani, and like that was the entire notebook.
I love
And
it.
yeah, I was like, wow, okay. So I would say I have kind of a couple pieces of advice I like give all students. And the first is to not get frustrated, because it's very easy, because the majority of my research is experimental. It's very easy to get frustrated, especially when things are failing in the lab. And experimental research, the majority of the time things are failing. And it's also very easy to internalize failure. So if you have an experiment and the experiment fails, it's very easy to internalize that as, I am failing, as opposed to the experiment is failing. And those are two very different things, right? Because experiments fail, and it has nothing to do with like you as a human being being a failure. You expect experiments to fail, like that's life. So it's really important to separate those two and to make sure that you don't internalize that. So that's one very common piece of advice I give a lot of students, especially in their like second and third years, because that's usually when students are really hitting that wall, because they're facing a lot of that. And then another piece of advice I give students is, to not let the negative news just overwhelm the positive news, because it's very easy to let the negative news kind of take over your psyche and then kind of blow off the positive news. So it's really important to celebrate everything positive and kind of allow the positive news to take a really good firm root in your brain and your emotions. And like negative news can be any negative news, right? It could be like, a bad grade. It could be, somebody saying something kind of snotty
Nasty
to you. Yeah, right. Like it could be like just negativity. And you tend, in general, right? And whenever somebody says something negative to you, even if someone says something positive, that negative comment, you tend to allow it to just balloon. In the positive comment, people tend not to allow that to balloon to the same amount. So
it's actually a very good point. You're absolutely right. We do that as humans. I feel like a lot of humans, or maybe it's just me or your students who are doing this.
No, it's there have actually been studies that like a negative comment has 5 times the impact of a positive comment. Yeah.
Really?
So, yes. So
Oh my God.
Yeah. So like you really need to focus on
the positives.
On making sure that the positives in your life, you give them focus, because the negative comments they're going to take your focus even if you don't want them to. So you really need to give the positives your attention.
Right. That's two are really, really great pieces of advice. Not getting frustrated and not letting the negativity take over the positivity. I think that's very, very important. Really looking forward to all your advice that's coming our way when you're taking over the account, honestly, because I'm loving this conversation. Well, Andrea, I hope it sounds to me that your research experience so far has been wonderful, and I hope it will continue to be wonderful in the future as well. However, if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here.
Yeah. So, I mean, I think one of my 3 wishes is the same wish every faculty member would wish for. And
what could that be?
Yeah, exactly. That would just be more funding. Yes. So I'm pretty sure every faculty member would get behind me on that. So probably my second wish would be more transparency in protocols. And that would actually be that would be both for faculty, but that would also be on behalf of all the students out there. I remember when I was a student, like really struggling with just reproducing things where, as we talked about earlier, there was like one missing step. And that would be just really helpful. And especially I look around now, like there are like YouTube wasn't like sharing protocols on YouTube wasn't as big of a thing when I was in grad school.
Mhm.
And that could be such a resource. Instead of having written protocols, having like video protocols. And I realize there are some journals like Jove that offers visual protocols, but it's also super expensive. And YouTube's free. So, we don't need like super fancy video protocols, like a cell phone and a student in a lab. That's more than sufficient.
Yeah.
Yeah. And then I think the third is, kind of reimagining this whole conference thing. So 2 years ago, so pre-COVID, I ran a virtual conference, but it was like a distributed network virtual conference. In other words, there were hubs. So it was almost like a local or regional in-person conference, but then all the hubs were connected. So then it had kind of a combination of hybrid because there were, virtual talks, but then also the in-person component. And a lot of the hubs had in-person poster sessions, but then the virtual part, all the speakers you could ask questions of all the speakers. So there was still that interactive global aspect. And I think that is super important, keeping the virtual conferences, because it really does enable a lot of students to attend conferences. It allows researchers from a lot of different countries to attend conferences, especially as things like visas are getting harder.
Yes.
And conference attendance is getting so much more expensive.
Oh, yeah.
And I think about especially my undergrads who over the last like year and a half have been able to attend, like maybe 3 talks at a conference, right? Like even if I could afford to send them all to a conference, they wouldn't want to go because they have classes, right? Like they can't actually go anyway. But now they can, see like 3 talks. And that's really useful for them. So keeping that as a possibility, I think is very important.
Yeah, absolutely. Yeah, all 3 wishes, very, very important. Funding, oh, big yes. Protocols, video protocols, yes. We need, and please write all the steps. It's very, very important. I mean, show all the steps or talk about all the steps, however you're doing it. As a researcher, because that is your work should be reproducible by another lab without having to bombard you with questions, and it shouldn't be a guess game, like a treasure hunt, like, oh, what could this step be? What could these parameters be? And also the hybrid conferences, I think that's very, very important. This has been amazing, Andrea, but before I let you go, one last question. I cannot let you go without asking about your learnings from the pandemic that we are living through. Whatever you can share.
Okay. So I would say I've had several different things I've learned. So one of them was really because the last time I ran the virtual conference, it was like pre-pandemic. And so I ran it really just to try to enable communities to come together. And so when we did it, so it was me and several colleagues actually from lots of different countries around the world. And we didn't anticipate it being as prescient as it ended up being. And then, so just seeing how important actually having virtual conferences ended up being, that was one thing I learned. Another thing I learned was that, travel is important, but, it doesn't have to play as big of a role as it does. So the year before the pandemic started, I think I flew like 100,000 miles traveling. Yeah. And then in 2020, I was scheduled to fly, like based on my travel schedule, I was scheduled to fly something like 130,000 miles. And then all of that got canceled, obviously.
Yeah.
And I was so happy, actually, that it all got canceled because I was really dreading it. And so I think now in the future, like travel schedules like that just aren't going to happen. Because a lot of that travel was travel to like Washington, D.C. to serve on panel review committees for various things. And a lot of those agencies are now revisiting those decisions to have all of those committees in person.
Right.
And that's going to make a huge change in, my quality of life, but other people's quality of life, right? Because it is super stressful to, for example, like take a red eye Tuesday night, be in DC for a day, and then fly back at 10 p.m. on Tuesday night or Wednesday night.
So
right? Like it's it's stressful. It's very like physically stressful on your body to do that. And I would just spend a lot of time sick, just ill because I was on planes so much, and it didn't matter like how much I tried to, you know, stay
Reduce it.
healthy. Yeah, I was just sick all the time. So I think that is like one of the big lessons I've learned is that, you know, travel is important, but being more picky about the travel I do, that's going to make a big difference in my life.
Right, right. I hope it continues that way, that it's also good for the environment. It's good for
Exactly.
people, it's good for environment, it's good for everyone. We just need to find a
Yeah.
balance. I mean, no, don't scrap in-person meetings or conferences or panels
Right.
completely, but pick and choose. You can't.
Yeah, pick and choose. And then a lot of the travel people did just, it wasn't really needed, right? Like it wasn't, and then maybe, you know, instead of doing as many conferences as we've been doing, maybe do fewer conferences. Like we don't need to have as many. Like it got to the point that there were conferences like every single month. Like, do we really need that many? Like, come on.
Probably not.
You know, and then we can also do a better job of organizing and like coalescing different events. So
yeah, quality over quantity. That is very, very important. Yeah. Well, thank you very much. This has been wonderful. Very, very much looking forward to your time on Real Scientist Nano. I had a lot of fun learning about you, meeting you, learning about you as a person, as a scientist, as a professor, and I'm really excited about your time on Real Scientist Nano. So thank you very much.
Yep. Thank you.
Thank you for listening. To know more about us, please visit our website, realscientistsnano.org, and follow us on Twitter at realsci_nano.